I believe this is the most important part of our today's lecture, because these definitions are there in textbooks. How do we use this definition and then understand what is going around? Is a vector space or not? That is where we have to interpret and then use our knowledge. So what I will do in each case is I will tell you what is the set of vectors, what is the set of scalars, and what is the vector addition operation, what is the scalar multiplication operation. Okay? So you have to tell me whether it's a vector space or not. So for that, what you have to do? You have to check each one of those axes. Okay? So let me start with my first simplest example. So vector space is also a set of real numbers. Field is also set of real numbers. Addition is addition of numbers. Usual addition. Okay. Usual addition. Okay, so normally I will not write this because it is a little bit boring to write every time. So I will say, if it is not usual addition and multiplication, I will mention. Otherwise, they are simply usual addition and multiplication. So will this form a vector space? Set of real numbers. Geometrically, this is a line from minus infinity to plus infinity. Every point on the line is a vector. So what will be the dimension of this vector space? Minus infinity to plus infinity. That is the total set. Okay, let me put it this way. I define the dimension of a vector space as set of number of elements in the basis. And basis is maximum number of linearly independent vectors that you can construct in this vector space. Correct? Intuitively, you can understand the following. To construct a vector, you require scalars. Correct? If you want to write in terms of the components, if you choose a basis, you have to take scalars. The number of scalars that are required to represent a vector is the dimension of vector space. If I want to represent a plane, I require 2 components. If I want to represent a vector space, I require 3 components. So each component is a scalar, right? So the number of scalars that are required to represent a vector is actually the dimension of a vector space. Sometimes, even though this I did not give you as a definition, but this intuitive understanding will help us to decide how the dimension of a vector space is. So now, tell me what is the dimension here? What is the basis for this vector space? Tell me one arbitrary vector. One. Just one number is one vector, that's all, because it's a real line. When I say vector, now you have to dislodge yourself from this arrow business, and then object can be anything, but a vector is an element of this vector space, that's all. It's a set. So every element of that set I will call a vector, that's all. So 1 is a vector, 2 is a vector, 1.2 is a vector, 1.25 is a vector, pi is a vector, e is a vector. All these are vectors. Now, what can be the basis? Any point can be basis, but in general, if you want to choose the real number, you want to use to make a vector as itself, then you choose the basis as 1. If you choose 1 as the basis, number 1 as the basis, You want to generate a vector alpha, multiply alpha with 1. You want to get a vector beta, multiply beta with 1. So scalar will be same as vector if you choose the basis as 1. If you choose basis as, let's say, pi, then what happens? If you want alpha, you must multiply with the scalar called alpha divided by pi. So that additional effort you have to take. So sometimes we call this as trivial basis. Trivial basis means that the simplest basis that you can take. So 1 is a trivial basis, but we have already said basis is not unique. So you can actually have any point as the basis, so that other vectors can be represented in terms of that as another scalar multiplied by that. Correct? So this is a vector space. So this algebraic structure R, plus, dot is a vector space. The basis, trivial basis, as a single element and dimension is equal. Why it is equal to 1? Because we can write only one vector. Any other vector will be linearly depending on that. So there is only one vector that we can write linearly dependent set. So it is 1. In my second example, let me consider V as set of complex numbers and F as set of real numbers and plus and down. Will this form a vector space? What will be the dimension of the vector space? 2, because I require 2 real numbers to represent one complex number. It's very fast to identify dimension if you know, if you understand intuitively how many field variables or scalars are required to make a vector. So this is a vector space. It's a 2-dimensional vector space. What is the trivial basis? Any 2 complex numbers can be a basis, but what will be the trivial basis? Trivial basis will be, you must multiply one scalar with one basis element, another scalar with another basis element to get an arbitrary complex number. I want to get a plus ib. So what should I multiply a with? 1. What should I multiply b with? I. So 1 and I. 1 plus 0i, 0 plus 1i. These are the 2 basis elements. Okay? Trivial basis is 1i. But as I told you, you could have any 2 complex numbers which are not along the same line, which are not linearly dependent, can become a basis. So let us call this as 2a. 2b, I will take the same complex number, but I will choose field also as complex number. I told you my field, scalar field can be real numbers or complex number. Now I choose field also as complex number. Then what happens? What is the dimension of this vector space? How many complex numbers are required to represent a complex number? One only. I require one complex number because it's like one real number to represent one real number. I require one complex a one-dimensional vector space. Even though complex plane, but since my field is also a plane, this is a one-dimensional vector space. So this is dimension of this vector space is 1. And what is the trivial basis? Just 1. Multiply everything with that 1, you will get the basis. Now let me consider set of all 2 by 2 matrices. So V is set of all 2 by 2 matrices. And the field is set of real numbers. And plus is matrix addition. Because elements, vectors are matrices now. Vectors are matrices. So plus is matrix addition. When I take one vector, it will be one matrix, another vector, another matrix. When I add, it will be matrix addition. So will this be a vector space? When I say field is real, components of the matrix are real. That's all. Field is real means components of the matrix are real. So is this a vector space? So when I am asking this question, at the back of your mind you must actually verify all the axioms. If I add 2 2 by 2 matrices, I will get another 2 by 2 matrix closed under vector addition. Matrix addition is associative, only matrix multiplication is not associative. Matrix addition is associative. Correct? There will be a matrix called 0 0 0 0. So additive identity is there. And for every matrix A, B, C, D, there will be a matrix minus A, minus B, minus C, minus D. Which means you have an additive inverse. Matrix addition is commutative. A plus B will be same as B plus A. So all those things are satisfied. You multiply with any real number a matrix, you will get again a 2 by 2 matrix. Distributive also can be verified. So all of them will be satisfied. So it's a vector space. In these examples it is somewhat trivial, so I didn't argue. But every time when I ask a question, will this form a vector space, you have to mentally argue that it actually satisfies all those axioms. Okay, so what is the dimension of this vector space? Four. One. Why is it one? How do we decide what is the dimension? Number of linearly independent vectors. So did we construct number of linearly independent vectors here? See, constructing number of linearly independent vectors starting from a vector space is slightly challenging, time consuming. That is why I already said that think how many scalars are required to represent a vector. That is same. With every linearly independent vector you might attach a scalar. So how many scalars are required? That is easy to intuitively guess, right? So how many scalars are required to write a 2 by 2 matrix? 4 scalars are required. So you have 4. About the dimension you can immediately guess. But I am going to ask the next question, tell me what is the basis. So that question may be a little bit difficult. Okay, the dimension of this vector space is 4. That means I must now write 4 2 by 2 matrices as the basis. Correct? 4 2 by 2 matrices as the basis. See, I am writing only a trivial basis. You can construct infinite number of non-trivial basis sets, but I am writing one trivial basis. So what will be the trivial basis in this case? Huh? Yes. So one matrix with 1 here, 0 here. Another matrix with 0 here, 0 0 1 0 0 0 0. Now suppose if I change a field as complex numbers, will there be any change in the dimension of the vector space? There won't be any change because there is no difference. Instead of 4 real numbers, you require 4 complex numbers. That's all. So if I write this set of 2 by 2 matrices over real scalars or complex scalars, the dimension is 4. Okay? So there is no change in the dimension. Basis. This basis also will work. Okay? But let me write that. So let me call this as 3A. And 3B, B is set of all 2 by 2 matrices. And F is complex B.